Now, the other aspect of this then is the kind of more clinical aspect, which is think about blood volumes and kind of blood concentrations and things like anemias. Now, hemoglobin deficiency, which is an anemia, is accompanied by generally a red blood cell reduction. And it conforms to what is routinely referred to as the supply and demand theory of people like Bassett and Howley, who published this in Med-Science, Sport and Exercise. Fundamentally, this is the notion that if I reduce red blood cell count and I reduce hemoglobin concentration, I fundamentally reduce my capacity to move oxygen to a cell and CO2 away from a cell. And therefore, the demand in the cell, even though the demand in the cell tentatively wouldn't have changed, progressively increases, because fundamentally I have reduced my ability, if I'm anemic, to get oxygen to the cell. In terms of anemias, there are three main causes. One is loss of blood. Second is decreased rate of red blood cell production. And the third is an increased rate of red blood cell destruction. And there are some big causes. I mean, one of the ones actually is fascinating, which is called a pernicious anemia. And in a pernicious anemia, it's actually due to a lack of vitamin B12. And we need vitamin B12 in red blood cell production, which, it may be quite surprising. And so if we have a B12 deficiency, what you end up with is a kind of a more, when you look at the red blood cell under the microscope, it's more opaque. It's less of that kind of very rich red in colour. And because it's more opaque, it's actually a reflection of a loss in its structural integrity. And if we lose the structural integrity in the red blood cell, its ability to deform under pressure changes. And actually, rather than being able to deform under pressure, as we talked about earlier on, they just collapse under pressure. And so you get a loss of red blood cells. We talked about a blood volume, loss of blood volume, as you might see in blood donation, for example. That is generally associated in some individuals with an anemia, and that's why one of the things that's often recommended after donating blood is to increase things like iron content to compensate. The flip side is the polycythemia. So polycythemia is an excessive production of red blood cells, and of course what we see is a polycythemia, particularly when we expose somebody to altitude. I mean, some very nice data that was published about 20 years ago now, where they exposed a group of athletes to altitude at Pikes Peak. Pikes Peak is in America. It is in Arizona. Sorry, not in Arizona, it's in Colorado. And it's an altitude of about 2,500 meters above sea level. And what they found actually was, we've looked kind of longitudinally in our altitude data in this session. What they showed is actually, if you look at on an hour-by-hour basis, they found us about a 300% increase in red blood cell production in the first 6 hours of exposure, because it's that instantaneous stress that's being put on the body which is triggering the hypoxic state. So you get this massive polycythemic effect, but actually you lose that quite rapidly as we start to become acclimatized to the hypobaric environment that one experiences at altitude. This kind of just reflects for us the stages of anemia, the kind of what's called the iron depletion stage, the iron deficient, then we get to iron deficient erythropoiesis, and then you get to iron deficient anemia. And you can kind of see the kind of effects here in terms of the standard scores we would be looking for in terms of our red blood cell counts, but also, which are these values here, but also the notion in terms of the role of things like ferritin and serum iron. So if we are iron deficient for whatever reason, and again we see this a lot at altitude, because it's much harder, despite the fact that you are in a hyperbaric or hypoxic environment, if you perhaps simulate it environment, it is much harder to retain iron, because it's much harder to eat. You start to lose muscle mass. There's all sorts of things going on at altitude. So it is often recommended that you supplement with iron. We also see similar effects in individuals who perhaps have a deficit in iron within their diet for clinical reasons. The net result is you need iron. Remember that the process of erythropoiesis is the production of red blood cells. And you need the iron both in that process, but also you need the iron to be on the hemoglobin molecule to allow the oxygen to attach to the hemoglobin molecule. So if we're iron deficient, then fundamentally you cannot get that interaction between the O2 molecule and the red blood cell molecule. The net result is you're carrying less oxygen, despite the fact that the demand is either as it was or is increased, for example, if we expose somebody to training. And this again just refers to kind of what is going on in terms of our processes, in terms of iron retention and iron loss. This was published a while ago in 1999, but it's actually a very useful kind of schematic for us, which shows us the process. So you can see here 1/3 of iron stores are in the liver, 2/3 are actually within things like myoglobin. So myoglobin plays an enormous role. Myoglobin is the kind of the hematological store in the muscle itself, and it allows us to store oxygen in the cell rather than actually within the circulation. Now, that's fine. But again, if you're iron deficient, then the amount of myoglobin where I can store oxygen in the cell will start to decline. We've got the hemoglobin molecule, and then the hemoglobin molecule which is on the red blood cell. Again, if I'm iron deficient, the amount of hemoglobin that is actually usable, because you'll have the heme molecule, it's the globin molecule where the oxygen is attached into. If iron is deficient, there are less of those globin molecules that are actually available. That then has a direct effect on oxygen consumption in the mitochondria. But the other thing to remember is that this process of red blood cell production actually comes from the bone matrix in the bone itself. So that fundamentally there's a connection here with between anemia and conditions like anorexia nervosa. And bone mineral density. So what we know is there is this condition which is often referred to as the female athlete triad, but it's also referred to now as red S, whereby if we have, for example, a highly suppressed nutritional intake for whatever reason, it has a direct effect on our bone mineral density. If we get a reduction in bone mineral density, we get a reduction in the bone marrow, and it is in the bone marrow that a lot of the red blood cell production is triggered from. So the net result is, almost even if I haven't got iron available, but if I have got iron available, but I've actually got a poor diet, the amount of red blood cells I produce will also start to decrease. And here's kind of a schematic that's again from that same paper, but it's a good kind of indication of kind of what happens if we've got a normal response. So this is kind of we take our ferritin scores, we look at our hemoglobin concentrations, these are what they are for males and females. So hemoglobin is normal, so it's a normal health check, and fundamentally you just do kind of normal monitoring. If on the other hand though, if we get changes, then one of the things that's often recommended is the first thing to do is go, well actually if there's a reduction in things like serum ferritin or hemoglobin concentration, we would supplement with iron. Because fundamentally, if I can supplement with iron, if that is the issue, fundamentally that will increase or help to increase the hemoglobin concentration. And again, the same thing goes on here, which is how we monitor that. And then if we've got really low serum ferritin concentration, which is our proxy indicator, we might use either an oral or intramuscular iron supplementation. And then what we then do is we kind of then put the patient into these different groupings depending upon what the responses are. This becomes a really important measure, and it's a routine measure that we do with endurance athletes, particularly high performance endurance athletes, but also we'll do with clinical patients.